Hey, Harry.
Hi, sorry to be slow.
Oh, that's fine. That's fine. Yeah, we still have time. Yeah.
Okay, cool.
Let me sign you as a co-host. Okay. Harry, you can share your screen now.
Okay.
Yeah.
Let me see. Everything okay?
Yeah, it works well. So we will start in maybe 2 minutes.
Okay, great.
Yeah.
Actually, I was you said 90 minutes, so well,
Yeah.
and
So yeah.
I fill an hour, and I left a little bit depending on you guys' style, whether you want to have lots of discussion, or I put in a little part at the end in case there's time or not.
Yeah. So we don't have a time limit, so you can decide by yourself.
Okay.
We also allow people to ask a question during the talk, so you may have a lot of questions.
Actually, okay. You said 90 minutes, so I fill an hour, and I left a little bit depending on you guys' style, whether you want to have lots of discussion, or I put in a little part at the end in case. I'm getting the recording back.
Yeah. We don't have a time limit, so you can decide by yourself. Okay, I guess now it's okay. Yeah. Okay. Yeah, maybe we can start now. Joey, can you record it? Yeah, we can start. Okay, everyone. Welcome to our Harvard CMSA seminar. Today, it's our great honor to have Professor Howard Hwang from the Stanford University as our speaker. So Howard got his bachelor and master degree at MIT, and he got the PhD degree from Princeton in 1997. Howard has made many important contributions to condensed matter experiments. One famous example is the discovery of the high mobility electron gas at the interfaces between oxide materials. One most recent example is the discovery of the Nicolaites superconductor in his group. This opened a new exciting direction in condensed matter. Also today, Howard will tell us about the recent experimental progress in Nicolaites. Welcome, Howard. Please.
Thank you. Sorry, let me see what I'm doing. So thanks very much for having me, and yeah, appreciate the opportunity to speak to you all. So feel free to ask questions. I think there'll be more questions than answers than at this stage of this work, but let me give a little bit of a survey. I'm going to focus more on the experimental side. Much of the audience here has been thinking about various theoretical scenarios. So let me focus on trying to be as clear as possible on the current experimental status of this system. So let me begin by acknowledging that we've benefited from an incredibly wide and great team of collaborators. I list at the top here some of the ones locally in my group that have been working on this. Some have moved on to bigger and better things, as you can see here. Other collaborators, lots of advice and guidance from experts in cuprate superconductivity. A fantastic collaboration on electron microscopy and spectroscopy. As you'll see, we've been working closely with a number of X-ray scattering and spectroscopy groups, as well as theory. So yeah, first and foremost, let me thank all of them for their contributions, without which this couldn't have happened. So I'm going to go right in, especially given the nature of this seminar series. I don't need to really pretend to introduce to you the background, and start right in with a basic question, which is fairly soon after the discovery of cuprate superconductivity. This is sometimes hard to remember how strange it was a place in terms of material space to find not just superconductivity, but high temperature superconductivity. People were wondering whether you could make analogies in other material systems. And so the specific one we'll focus on here is thinking about layered nickelates. And the basic question could be phrased as, can you make this layered nicolate look like the parent compound of so-called infinite layer cuprate superconductors? So the starting point, just in terms of oxidation state and whatnot, is we're trying to go from copper to nickel. So we want to go from copper 2+ to nickel 1+. It's a very unusual oxidation state for nickel. And quite a long time ago, actually, this is a 1999 paper. My understanding is these ideas were floating around in the field even before that. These two were the first papers I'm aware of asking this question explicitly. So indeed, if you are able to synthesize this layered nickelate compound using a lanthanide as a spacer layer, then you do get a nominal D9 configuration. So this looks very analogous. And that was the starting point of this first paper. And subsequently, Warren Pickett and Lee here pointed out an important feature that we'll come back to here and there in the discussion, which is that actually this is not a complete analogy in the sense that there are big qualitative differences in the electronic structure. And so in the LDA limit, for example, what they find, and this is pretty much the consensus of quite a few more electronic structure calculations, is that you have a cuprate-like large Fermi surface of dx squared minus y squared character. But in addition, you have these electron pockets. There's one in the zone center in the absence of Coulomb interactions that also appears. So it's already kind of quite interesting and rather different in the sense that, that you have these two bands, and there's a certain degree you can consider this a self-doped system in the sense that you have charge balance, say, between the electron pockets and the whole occupancy. So in terms of getting to this monovalent nickel state, this is, as I said, quite unusual if you're familiar with material science or chemistry issues. And the work we're doing is building on several decades of rather creative chemistry, sometimes called the soft chemistry techniques. And the specific one we'll be utilizing was first seen in or discovered in 1983. And the idea is as follows. Let's start with the perovskite form of the nicolate. They studied lanthanum nicolate, so nominally 3+ nickel. And one can do a series of deintercalation reactions where you can pull out rows of oxygen. So you can go from 3+ to 2+ and kind of stabilize this brown millerite phase. And you can go further from 2+ to 1+ by taking out this other apical oxygen row and make this infinite layer structure. So this bulk chemistry itself is actually quite challenging, and people are working and actually making exciting progress to this day on this problem. A second key development in 2009, again, we will utilize, was the observation that you could perform these reduction reactions and have some benefits of stability in oxide than film heterostructures. So to give you just a kind of eye candy of how this looks like, so this is a picture inside of one of our chambers. we're using pulse laser deposition, and for the last 2 decades or so, we've been working a lot on making artificial heterostructures where we try to get down to fairly precise atomic control. So this is a fairly, elaborate and somewhat expensive technique. As I'll discuss later, the nickelates have now been stabilized by a number of groups. We're using pulse laser deposition, but also by molecular beam epitaxy and so on. So this is how we're growing the perovskite precursor phase. And as far as this reduction reaction, it looks much more modest, but it's actually quite challenging in its own right. This is how it looks like. This is 2.5 by 5 millimeter thin film, loosely wrapped in aluminum foil. And these pebbles down here are calcium hydride, and we're using that as a reduction reaction reagent. Right? So we vacuum seal this in a glass tube and do a fairly low temperature reduction anneal to, again, pull out these planes of oxygen. So I thought it was worth giving credit to the origins of this work in our group, and just to say that this has been a long process. So we started this quite a number of years ago, and a postdoc at the time, Hwang, had nicely stabilized these sorts of undoped films, but we could never quite get it reliably doped. And so we tried a number of gating techniques or controlling the oxygen stoichiometry, but we were never able to dope it at that time. I should say she's doing well despite these challenges. She did other lovely things. But in the process, there was very little known about this material. It was yet fairly understudied. And so we started to do spectroscopy studies of the parent compound. And we had a fairly lucky accident that just as that started to look interesting, a subsequent postdoc, Denver Lee, he's now at City University of Hong Kong, kindly stepped in to try to both provide samples and revisit this issue of doping. And so the doping approach that eventually worked was a lucky accident in my own history. I was a summer student at that time in 1993, 2 and 3 at Bell Labs, and we were looking at this perovskite nicolate. It's already quite interesting. It has a very dramatic first order metal insulator transition from a high temperature paramagnetic metallic phase to a low temperature, ordered antiferromagnetic insulator. And we had fooled around a little bit with doping this system. And it's ironic that, some 25 odd years later, we came back to this issue of trying to use substitutional doping. So the idea was as follows: let's chemically dope the perovskite phase first, and then reduce it hopefully to the infinite layer phase. And that might be the way we can approach systematic carrier doping. So it eventually worked. This one slide summarizes a ridiculous amount of effort, actually, but just to give you in pictures the issues we faced. So we started with something that in the cuprate analogy, we might hope to be nominally superconducting, and we start to see the onset of a superconducting transition. It's yet far from complete, as you can see here. And if we look at this generation of samples, what we find is this was our perovskite nicolate. We tried to reduce it. And most of what you're seeing is completely second phase decomposition products. It's kind of a mess, actually. And just at the interface, there's a sliver of what eventually we could identify as a superconducting phase. That is this infinite layer structure. So with some effort, we could expand this infinite layer phase regime. And what you can kind of imagine and see here is that the substrate gives you a director, if you will, or a proximity effect to stabilize the phase that we want. So the basic issue is that if I take the perovskite and I want to, in bulk form, and I want to de-intercalate planes of oxygen, I have a degeneracy, right? I can take all different cuts, and the substrate helps break that degeneracy. And so we see a proximity effect of on the order of, 5, 10 nanometers or so from the substrate. And so the last key step for us was then to make a perovskite heterostructure and further cap it with, in this case, the substrate is strontium titanate and more strontium titanate on top. I should mention in our reduction conditions, that component doesn't do anything. And so we get this proximity effect from both sides, and we can stabilize, depending on the details, somewhere between 10 to 15 nanometer thick single crystal infinite layer nickelate. So if you're interested in these details, we discussed this in this paper, but schematically what you see here is that idea that we're deintercalating these planes of oxygen, stabilizing these thin films, and indeed this system becomes superconducting. So let me start with a kind of a summary of some of the basic properties that we see. Let's start from that perovskite form. You see that the resistivity of the neodymium nickelate, nominally undoped system, has this well-known first-order metal insulator transition. And as I previously alluded to, consistent with old results, that if you whole dope the system, you suppress this metal insulator transition. And if we go from O3 to O2, we find something rather different. The undoped system is kind of intermediate. It's neither really a good metal or an insulator. You have this weak, approximately logarithmic upturn, but for the dope compound, you indeed see that this thing goes superconducting. In terms of the basic properties that we find at that time, you could see a nice critical current density. I should say that now with subsequent materials improvements, we're at about 1 to 1.5 megamps per centimeter squared. If you take the magnetoresistance near TC as a measure of the Ginzburg-Landau coherence length in plane, it's about 3 to 4 nanometers typically, what I'll show you. And in terms of the magnetic response, we use two cold mutual inductance measurements. And if there's time at the end, I'll come back to this point. But the details aside, what we then would deduce is a London penetration depth on the scale of a micron or so, quite long. Okay, so let me try to give you our current understanding of some of the basic features of the electronic structure. And the starting point might be to revisit the motivational kind of story of this effort, which is that is there any difference between these two D9 electronic configurations? And indeed, it's actually quite different. It has a lot to do primarily with the orbital energy level alignments in the cuprates, right? We're 1 over on the periodic table. We're in a lower oxidation state. And so let me just give you a cartoon summary of the cuprate landscape first. So in the cuprate problem, right, we're starting from this notion of a charge transfer insulator. And so you have a lower and upper Hubbard band, primarily of dx squared minus y squared origin. And then you have kind of this band of oxygen, if you want to use this language, such that when you whole dope the system, what's rather interesting is you're actually kind of having something with holes of character coming out of the ligand field, right? So this notion of a Zhang-Rice singlet from the early days of cuprates gives you a nice understanding of both the nature of the doped hole, but the coupling to, say, magnetic fluctuations and so forth that's so relevant for that problem. In the nickelate case, the starting features are rather similar, but there's an additional ingredient, namely, the first statement is that where things align look rather different. So the nickel 3D band is split, nominally similar to or above the oxygen states. And you're also kind of in the midst in the upper Hubbard band regime in a manifold of bands derived from the rare earth or lanthanide 5D electronic states. So that if you dope in this system, you have an interesting kind of additional degree of freedom. You can kind of see this from early Vanier kind of projections of electronic structure calculations from Tom Devereux's group in this paper, where we have the cuprate-like formation, right? There's still quantum mechanical hybridization, but we have in addition electron-like states that have a much more 3D kind of extent. And this corresponds to, in Warren Pickett's paper, these electron pockets, right? So I won't go into the details, but this kind of picture was framed from various spectroscopies, X-ray absorption and RICS, as well as electron energy loss spectroscopy and electron microscopy. So just to highlight one of the features that's relevant is that if we take nickel oxide or the perovskite nicolate, and you look at the oxygen K edge, you see this strong, well-known pre-peak feature that's associated with these contributions. But if we go to the infinite layer phase of lanthanum or neodymium, this is largely absent. So this is XAS, and similarly in eels, you can see this dichotomy between the perovskite and the infinite layer phase. The other broad statement, these are kind of very approximate statements, of course, and some debate going on in the field still, but this is closer to an intermediate or approaching the Mott Hubbard regime in terms of this band alignment, as I just sketched for you in the previous slide. Okay, another important early question that arose, and in fact, I think, let me see, in fall of 2019, I was visiting Harvard. I had given a talk on some of our initial results, and I had spoken with Yahui and Ashvin, and they and others were thinking about the nature of the spin state of these holes. And so we went to look at that in some detail, and the summary statement is that the holes appear to be in the low spin state. But the system is rather interesting because you're fairly close to the triplet state. And just to illustrate what I'm talking about here, the question is, you know, if I just take these top two levels, if we remove an electron, where does it come from, right? And so you may think that we take the topmost electron. That's what we seem to find. That's in a regime where the crystal field splitting is the largest energy scale of the problem relevant for this question. But of course, you are very close to being in a regime dominated by Hund's coupling, right? That you'd rather take this lower electron out in order to maintain Hund's energy. And so if we look at, say, a dope versus undoped nicolate in now nickel L-edge XAS, we can conclude that we are predominantly in the low spin whole dope state. Okay, so and then our initial look at the phase diagram and the doping dependent structure was looking at this now neodymium strontium system where we spent a lot or most of our energies. First statement is we see a dome of superconductivity. And I compare this with the 214 cuprate system, so it's rather qualitatively similar. What is different, though, is that we see weakly insulating behavior on either side of the dome, right? These are the raw resistivity curves, and really there's not that much of a spread. Let me also say that this was also around the time of the first independent group working on the system. So this is from Ariando's group in National University of Singapore, who had very similar lovely data. The point we wanted to emphasize or think about was, at this point, a phenomenological observation that if we look at the low temperature normal state resistivity across this doping series, you would see that there is a relative minimum, and this dashed line across here is the scale of a quantum of resistance per nickel oxide plane. So qualitatively, what you can think of is that just when we dope or dip into a regime approaching coherent transport, this correlates with the superconducting dome. So I want to come back to this, revisit this problem later on. So let me not go into the details here. So another central question, thinking about this comparison between nickel and copper, is whether magnetism or magnetic fluctuations are relevant. And so this is a real challenge, of course, because as I'd alluded to, that we can only stabilize, I think the community at this point can stabilize superconducting films that are kind of limited to of order 10 nanometers in thickness, right? So doing things like neutron scattering, inelastic neutron scattering is quite infeasible, but we're fortunate that there's been great progress in resonant inelastic X-ray scattering. So this is photon in, photon out process, and this gives you access to dispersive bosonic excitations, and we're using that here to look for magnetic fluctuations. The starting point is that, again, there was not much known in this field, but at least by powder neutron diffraction in lanthanum nicolate and neodymium nicolate, no magnetic order was seen. So what we found was actually quite interesting in the sense that we found dispersive magnetic excitations that look very much like what you would expect for a spin wave dispersion in an antiferromagnetic square lattice. Now, I should say that we, and there's some technical challenges using resonant elastic X-ray scattering, magnetic X-ray scattering to really, on resonance, we don't have the wavelength to be able to access a clear statement whether or not there's long-range order, static long-range order. But clearly in the excitation spectrum, you see something very reminiscent. So if we look at this, these excitations in some detail, we find two things. You can reasonably fit the paramagnon, let's call it dispersion with two neighbor magnetic model. And we can compare that with the cuprates for J1 and J2. And in broad strokes, this is for undoped parent compound cuprates. What we find is a magnon bandwidth in the Nicolate case of order 200 MeV, which is somewhere between 50% or 75% or so of the cuprate magnetic energy scale. The second thing that we see here is that our magnetic excitations are quite broad, right? So in the cuprate case, these are generally resolution limited in terms of a RIX experiment. In our case, we're quite a bit above our instrument resolution. This is roughly the half width at half maximum. This dotted line is the experimental resolution. And you can see that they're quite broad. And if you dope the system, you can kind of chase the dispersion relation a little bit further down, but this rapidly just damps out. So that it's very hard to distinguish experimentally what's going on. So in summary strokes, the magnetic excitation spectrum of the parent compound of the Nicolaites looks rather similar to the doped cuprate, actually. And we suspect that these electron pockets, for example, are contributing to damping in the system. Okay. So, we and others looked around at other related systems. In particular, we had done an extensive series of looking at, say, the original neodymium versus praseodymium and lanthanum. These are the three kinds of systems that we can stabilize. And in all cases, we see a dome of superconductivity. And I forgot to mention that the same kind of epitaxial stabilization that's helping us make single crystal thin films is also straining the thin film itself. And so one can project all the variations effectively just to variations in the C-axis lattice parameter. And we see a kind of a generic dome of superconductivity here. I won't go into the details, but one of the ongoing discussions in this community has been whether or not 4F electrons are essential, at least for the occurrence of superconductivity. And I think we can say that that's not the case. For example, no 4Fs in the lanthanum. There are interesting features I won't really have time to go into, but we can first order say that this is dominated by ionic size and hybridization effects. A recent development in this field has actually been the observation of charged stripes. And so for, I guess, the focus of this series, this again is a very familiar concept to you. So let me just flash work of Matteo in a slide here. Again, looking at RICS, the basic feature is that we see something at about a third wave vector, a charge peak. It's interesting that as we look at the undoped, in this case, we were looking at lanthanum nicolate, and we look at this resonant scattering, you see contributions actually both at the nickel L edge as well as a lanthanum M4 edge. But as we dope into the whole doped and superconducting direction, this projects primarily to the nickel lattice. So we have apparently a charged stripe. There's approximately 1/3 superlattice vector. And this is roughly in the lanthanum case how it looks like, that this intensity comes on and it's coming down as we enter the superconducting dome. And I should say that just around the time that we put up our work on the archive, there were 2 other studies of the neodymium Nicolate system that showed also these sorts of stripe features. And it's interesting actually, because the stripes here do look quite distinct from those seen in say the 214, or as I'll come to, other layered nicolate compounds, and that those are kind of these diagonal stripes, right? Shown by electron microscopy and neutron scattering and other techniques like at Brookhaven. And so this is oriented in the high symmetry 1.0 direction, and it doesn't apparently disperse very much as a function of doping until we lose visibility as we enter the superconducting dome. So if we take a step back, we're building a picture of having a rather similar landscape to the general instabilities in other strongly correlated superconductors, and of course, in particular, the cuprates. So the stripe phase, first seen by John Tranquata in the cuprate case. And as I'll try to spend a little bit of time on going forward, this very complex phase diagram, we see this dome of superconductivity. We don't have this antiferromagnetic mod insulator as a parent compound, but we clearly see that magnetic fluctuations are important and a fairly large energy scale in the system. And so these notions of competing or intertwined orders that are so prevalent in the cuprate discussion seems very relevant here as well. So let me say a word or two of kind of the further expansion of this materials family. So much like in the case of many layered transition metal oxides, you can make all different kind of stacking sequences and kind of a family of materials. I think maybe the first discussion of this in the Nicolate case was from this paper in 1992. The idea was as follows, that you can make, much as we had done the perovskite version of these Nicolaites, or the Ruddleston-Popper series of these Nicolaites with, say, 1 layer, 2 layer, 3 layer, and so forth, right? So this is the 214 cuprate structure. And by deintercalating these apical oxygen planes, you can go into a family of layered Nicolaites. And so if you're not familiar with this terminology, infinite layer, this is simply denoting this is in the case where this kind of repeating compound formula goes to the limit of n equals infinity. So actually this notion again has been around before. So for example, a group at Argonne, John Mitchell and others have been thinking about this problem for quite a while. And so they had looked in detail at the 3-layer system. Recently there at Harvard, Julia Mundy's group has looked at the 5-layer version of this. And so let me first say that this is an interesting system in that you don't need to chemically dope it in some sense, that if you look at this stacking sequence, you can kind of think of this rock salt layer as doping or transferring charge into the nicolate compound. And this is actually taken from this Nature Physics paper from argon, right? Predates the observation of superconductivity that I told you about just now. And they'd actually speculated that indeed, actually, I'm not sure if I took this figure from here, sorry, that perhaps what they were finding was that they were in the overdope phase, right? That this natural kind of structural doping, if you will, took them beyond the superconducting dome. And so they also looked at different versions, say lanthanum and praseodymium and whatnot. And what they generally found was either a metal or a density wave insulator as their ground state. And again, recently, using MBE techniques to stabilize the 5-layer compound, indeed, this system was found to be superconducting. So we start to have kind of a growing materials family, much as you might find in the nickelites or the cuprates, of different kind of layered structures, all built up on the nickel O2 plane as the fundamental unit. So let me try to take the remaining time to tell you about recent developments we've been working on. Just highlight 2 efforts that we've been pursuing. So one of the challenges, we, of course, are very interested in probing the intrinsic electrical transport properties, but this is quite a mess in this problem right now, in the sense that there are still quite a few extended defects that we believe are dominating some of the spread and resistivity found in the literature. So this is just some of the early papers from a number of groups, including ours, in the neodymium strontium system. And what you can see is that this is our work, various versions. You can see that the scale of the resistivity is kind of varying by a factor of 40 or so. And even in our own work, we can find that there's quite a bit of kind of order factor 2 variation sample to sample that we think are arising from these extended defects. Okay. So what are they? If I look in detail at one of these boundaries, sorry if these boxes are actually making it harder to see, but let me just illustrate it here, that we have a fairly generic instability to making these so-called Ruddleston-Popper-like integrals, right? So it's this motif that I showed you in this layered family building blocks. And of course, you can ask, well, isn't this just a matter of delivering the right stoichiometry? But we think it's much more than that. And the issue is that we're growing this perovskite phase in fairly extreme tensile strain. And so the system is trying to address this strain by inserting these intergrowths. And these are basically frozen in from the perovskite compound going into the infinite layer structure. And so in summary, what we find is a lot of, let's say, bulk volume measurements are quite robust in the presence of these defects. Certainly for things like transport, this is the likely origin of the scatter that I just mentioned to you, or one of the important contributors. And so we've been trying to work on using or moving to a new substrate, colloquially known as LSAT. It's a little bit complicated. The point is as follows. Everything I showed you so far was on strontium titanate. And it's really this kind of question of how do you balance the competing materials aspects at play. So you can grow the perovskite phase under large tensile strain. And then if you reduce that to the infinite layer phase, should be, in principle, fairly close and lattice match to what it would ideally want to be. But you pay a price of these extended defects, as I just alluded to. But if we then compromise in a different way by going to LSAT, we can make the perovskite form a little bit more energetically happy, but then at the price of going to compressive strain in the infinite layer compound. So it's a little bit of this push-pull kind of business, but in terms of this extended defects, what's exciting is this largely eliminates them, right? So we can now grow nice films where we see no apparent extended defects largely across the film. I should say that the first report of thinking about different substrates for the proscenium system was this reference here on the archive. Okay. So what does that buy you? Well, hopefully it buys you a little bit more fidelity in the resistivity and other transport studies that you might want to do. And just taking this comparison directly, so you can see here the resistivity of this sample on strontium titanate. So it's quite a bit higher. You do see a superconducting transition, but by moving to LSAT, we have much higher crystallinity. And I'm going to spend some time talking about work that we've recently posted. So going back to this question I told you about from early days in this work, that we had this kind of observation that there was a resistivity minimum in the normal state that corresponded to the superconducting dome. So you can ask, is this really an intrinsic dome, or is it actually a manifestation of disorder, right? And so now by moving to LSAT substrates, we can grow kind of across the superconducting dome, and the low temperature normal state resistivity is quite low, and it's comparably low across a very broad range of doping. So we're kind of a factor of 5 or 10 below this kind of, a scale approximately of KFL equal 1. So I'll go into some of the details. I'm sure this is too busy to look at, but again, the scale of the resistivity of the whole problem has moved down. And in terms of superconductivity, first statement is that there's still a dome, but it's grown a little bit, right? Both in terms of TC and the width of the dome. It's actually quite surprising, or maybe at this point a coincidence, we're not sure, but now that the breadth of this dome is almost identical to that in the 214 cuprate problem. So, we think that this is now giving us an opportunity to take a first look at the normal state resistivity, hopefully more in the intrinsic regime across the dome. And so let me summarize things here. There's still, of course, ambiguity as the usual story for this kind of business about how I subtract off the residual resistivity and the functional forms. So what I'm plotting you here is the derivative, the slope of the resistivity as normalized to the room temperature value. So this orange business is where the slope is the same across or varying temperature. And so we have this narrow sliver of approximately T linear resistivity. And I show you that here for these two samples near this regime. So these light blue curves are the resistivity as a function of temperature. And what's quite remarkable in my mind is that that slope in real numbers is very close to that of the 214 cuprates. Right. So for example, this is like 17.5% nominally. If I compare that to 17% doping in 214 cuprates, it's virtually identical. So these are the slope values, if you're interested, in milliohm centimeters per Kelvin of the Nicolaites, as well as some cuprates in this linear regime. Now, to give you kind of a qualitative first look at the underdoped and overdoped regime. Looking first in the underdoped regime, I make this comparison again to changes in the crystallinity by moving between substrates. So it was originally higher. The scale of the resistivity has come down, but the qualitative features, and namely this resistivity upturn, is fairly robust, right? So that's still something that we observe. And I'll say more about that in a slide or two. If we look in the overdope regime, again, let me start with our previous samples on strontium titanate. This is divided by a factor 4. You see that there is this resistivity minimum, but this is almost completely suppressed on these new substrates, right? Modulo small features and magnetoresistance and so forth, this nominally goes to a t-squared behavior all the way down in this regime, as I indicated by this dotted line. So let me spend a slide more on the underdope regime. It's rather interesting. So I told you that this upturn feature seems fairly robust to the disorder that we were seeing, or the variations in disorder induced between substrates. So here's at x equals 0.05. And this is now just entering the superconducting dome, but you can still see that upon suppressing superconductivity by magnetic field. And we can plot this resistive upturn. It's really coming down as you enter the superconducting dome. What we found was actually kind of interesting, is that if we look at the Hall coefficient in detail, here I just show an example for a 7.5% doping. This is the same resistivity on a log temperature scale. This is the upturn. If I plot the Hall coefficient, I'm flipping it over here, this really tracks it 1 for 1 as we go to this low temperature regime. So it's a bit of a long story, but if I take kind of a 2-band picture and analyze the different possible scenarios, you can find the details in this archive paper. We conclude that we're basically apparently locking up the Hall carriers. We can't quite distinguish whether it's a density versus mobility contribution, but that density mobility product of the Hall channel is clearly freezing out in this problem. And what's left in the transport is electron-like character, we think, coming from these electron pockets. And so this is very suggestive that perhaps the correlations are locking up the Hall carriers. And one candidate, again, both in the cuprate problem and in our case, might be that these stripe instabilities are what's driving this transport upturn that we see. Now, if we look at the Hall channel, this is just the same phase diagram I showed you previously in terms of the slope or the derivative of the resistivity. If we look at the Hall coefficient, let me just show you the raw data here first. I want to plot 2 features of interest. One is this kind of local maximum of the Hall coefficient in the underdope regime. This is a thing that tracks the resistivity I told you about. If we take that local maximum, this gives you this line of points here. And the second feature is if we look at the sign change in the Hall coefficient, right? This kind of zero crossing across the series. These are these green squares across the top. So, this is very suggestive. We don't actually know at this point whether or not this is a coincidence of this multi-band structure, but certainly there's a lot of action going around the superconducting dome, and we can summarize all of these transport features in this phase diagram. And so to say again, we see an upturn in resistivity that we think might be related to this stripe instability. And I should mention that this is actually qualitatively also somewhat similar and reminiscent of the log T-like upturn seen in 214 cuprates. And for example, in high field magnetic field studies to suppress superconductivity. It has a similar kind of phenomenology. We find a narrow band of T linear resistivity near the peak of the dome. And then something that looks like it's headed towards a more conventional Fermi liquid in the overdope side. As I mentioned, this upturn in resistivity tracks this maximum or change in the Hall coefficient and the sign change. And so certainly for this crowd, I don't think I need to really go into all the different scenarios. I think I just focus on the data. It's certainly reminiscent of discussions of kind of competing orders, right? Possibilities of criticality that's been much discussed and debated in the cuprates. Let me simply say that this phenomenology, as we improve the materials quality, is approaching rather closely that of the cuprates. And this is despite some significant differences in the chemistry, in this intrinsically multi-band or self-doped electronic structure, in terms of being more in the Mott-Hubbard regime versus the charge transfer regime in the cuprate problem. And of course, this fundamentally different parent ground state. So yeah, let me conclude there. I guess I have a bit of time, so I maybe can squeeze one more thing in. But just summarize that the layered nickelates are an exciting new family of unconventional superconductors. There are aspects of correlation effects that are reminiscent of the cuprate problem, as well as intermetallic superconductors. A key qualitative difference here is that the charge reservoir layer of the cuprates is much more active in this case. It's not simply a source or sink of charge, but it appears to be actively hybridized in the relevant electronic structure. And we think this is leading to some of the important qualitative differences in the doping response. So there are many open questions, of course, in terms of how high can TC go. We're very interested in trying to study in more detail the nature of the undoped parent compound phase. There's also this question of pairing symmetry. And so if all of you are okay with this, let me spend a few slides then to tell you what we think we know about this problem, or what we can say at this point experimentally. Okay, so, what is the pairing symmetry of the nickelates? That's, immediately lots of theoretical efforts. Sorry, some of my references don't appear here. A number of studies using random phase approximation, TJ models, and so forth conclude that the dominant pairing channel should be dx squared minus y squared symmetry. There have also been other scenarios proposed.
Hey,
yeah.
Harold, I think someone is raising his hand. Daniel, I think you can ask a question.
Sure. Sorry, I didn't.
That's fine. Daniel?
I actually better ask it after the end. Better after the end. It's not necessary to ask it now, actually. It's
Okay. I just have like 3 more slides and then I'm happy to discuss.
Okay, very good.
Yeah. Okay. So, right. So these questions were around, as well as an STM study that suggested that both kind of, V-shaped and more fully gap-looking structures could be observed in spatial variations. And so we were interested in trying to go after this and using two-qual mutual inductance measurements. So we, have the challenges again being in this thin film geometry. And a lot of what we built was some version of the approaches taken by, many groups, but also Bozovich's group at Brookhaven, in terms of having a drive coil and a pickup coil in order to directly measure the complex conductance. And so our TCs are a little bit on the low side. And so in order to try to go to the low temperature regime, to make our best statements that, as far as we can, about the possible implications of symmetry, or at least whether or not there are nodes, we're doing these measurements down to Dilfridge temperatures in this kind of a system. Okay, so how does the basic data look like? So I'm looking just now at the optimal doped compounds for the 3 different families of the infinite layer phase, so lanthanum, praseodymium, and neodymium. What I'm plotting you here is so 1 over lambda squared, essentially, at the onset of superconductivity. And what we generically see is quite familiar to other thin film or these sorts of measurements, that we see the onset of superfluid density after we've reached a resistive zero. After some materials effort that I alluded to, we're now in a regime where we can start to see signs of a bit of a BKT-like discontinuous jump. So BKT temperatures are estimated by these circles here, and we see a reasonably clean peak in the dissipative channel as well. Right? And so, believe it or not, this was many years of work also just to try to get the materials to be of the fidelity to make these meaningful measurements. Maybe one thing that I forgot to mention is the scale of our coil is on the scale of 0.4, 0.5 millimeters. We're still constrained to a relatively small area thin film samples. And so, the challenges of having homogeneity on a larger length scale and so forth is really what underlies this kind of work. And just in maybe one last slide, then let me show you what we can say right now about the low temperature regime of the superfluid density. Here in black are the data for the 3 different samples or systems that I want to tell you about. And the red line is kind of a fully gapped type of fit. Obviously doesn't really fit very well. This is now just looking at the bottom third of TC. And what we see fits well is what we're calling a nodal fit. And so again, for many of you, this should be reminiscent of early days in the cuprate problem. Namely, it's consistent with a nodal with disorder kind of response as parameterized in this case by this kind of T squared over T plus some temperature scale, where this is of order kind of a third to a half TC in our case. This is kind of similar to what people saw in, let's say, dirtier early days cuprate superconductors. Now, I should say that actually, in terms of a fully gapped fit, that does a reasonable job for the neodymium system, but we clearly now understand that this is the onset of neodymium magnetic contributions. And so, unfairly, without giving you the long story behind that, we don't think that this is really what's going on here, right? We're doing a kind of picking up everything in our pickup coil. And so this is coming on from the onset of magnetic susceptibility of the neodymium moments. But so our current story is that our results are indicative of the nodal gap. Forgive me, there's another paper on the archive from another group that has qualitatively similar data, but their interpretation is a little bit different from ours. So I encourage you to take a look if this is of interest. So let me then really stop there. I'll just go back to my conclusion slide and take any questions. Thanks very much. And Daniel.
Yeah, actually, theoretically, for me at least, actually, one of the main difference with cuprates is that cuprates are negative charge transfer gap, so there is a lot of action on oxygen holes and so on. Mm-hmm. Whereas these ones, as you stressed yourself, are Mott-Hubbard type. In this case, actually, again, you yourself mentioned that if you go to nickel 2 plus D8 configuration, then triplet state S equal 1 can quite compete with this spin 0 state. Mm-hmm. Are there any experimental indications whether indeed at least proximity or a role of this triplet state? It was discussed in cuprates also, but in cuprates, because of negative charge transfer gap, it's probably less relevant. Here it might be very relevant. Are there any experimental indications whether it's indeed important for something? Are there some excited states which can be attributed to this triplet state and so on? in spectroscopy?
Yeah. So indeed, this question has been lively in the Nicolate problem as well. I had showed some work from Ashvin's group, and I think Monica and George at UBC. There's also been work from Kotliar's group worrying about this. And so indeed, it looks, at least theoretically, very close in energy. All I can say is that in terms of directly looking at this problem, we probably haven't looked extensively enough. But in terms of, XAS looks like it's quite dominated by the low spin state configuration. I would say, okay, let me show you one thing, but I'm not completely sure this is germane to your question, to this question, but anyway, let me show it anyway. Shoot, how do I get to? So, okay, I don't think I have the right slide at my fingertip, but this is looking at the superconducting upper critical field in a specific neodymium nickelate sample. The title is kind of the bottom line story. It's interesting because it looks unusually isotropic in terms of Hc2, and it roughly corresponds to poly-limited superconductivity. The point I was just going to say is that if we put the magnetic field in the plane direction, this is how Hc2 looks like. Okay, and the point is that this thing looks like it's poly-limited, but with an enhanced moment, if you will, right? So if I just put that in by hand, this is something like giving you about 2.5 Bohr magnetons. So I'm not sure this is really relevant to your question, but that would be one of the possible manifestations we might see, that we're getting close to seeing a nearby triplet situation. But again, I'm not sure that this is really coming from that kind of an origin.
Well, this neodymium also has magnetic moments. That
Yes.
may interfere somehow.
Yeah,
Would be better.
Yeah, working on it. Yeah, in the case of lanthanum, though, the moment is much less enhanced. I forgot the number off the top of my head, but yeah. Mm-hmm. But I would also, maybe I can take advantage and solicit, where else should we look in thinking about this?
Maybe some excitations.
Yeah.
Should be not very high in energy in principle, if indeed this, nickel 2 plus is really very famous stable S=1 state. That's
right.
Of course, here you don't have apical oxygen, so in principle, this non-cubic crystal field PD might be much larger. Mm-hmm. So that's why it can stabilize low spin state, but high spin state might be relatively close, I think. But where to look at it, I don't really know. I thought that maybe you thought of that, and maybe you saw some indications that it's.
Yeah, so the other thing I can say is that if you go back to this Rick's kind of study, so these are this kind of main features that I summarized in the discussion. I can also say that you can pick up kind of the highest energy optical phonon mode. It's a little bit hard to see here, but it's kind of flat going across here. There weren't any other very obvious excitations, at the current resolution limits of Rick's, or what we can say. But certainly this would be another place where we could think about, whether we see something. And I should say that people have also asked whether or not, these dispersive excitations might have different character than simple magnetic excitations, right? And so I guess these would be the places spectroscopically we would imagine finding these sorts of features.
By the way, maybe not directly related to that. What about Raman? Was it studied, and is there anything interesting in Raman?
Yeah, we tried, or let me see, Rudy Huckel's group has tried. What we mostly learned is that both strontium titanate and LSAT has a very strong luminescence that swamps everything.
Okay.
So yeah, so a fair amount of data, nothing that we can say robustly at this point because of that constraint. Yeah.
Okay, very good. Thank you. That is very nice story in principle. Very good.
Yeah, thanks, Harry. I actually have a follow-up question. So, do you think it's possible to tune this state from low spin to high spin? Maybe you could just tune the crystal field splitting in some way.
Yeah, certainly. That's a very interesting direction, right? Which is that whether via substrate strain and so forth, one could go after these things. I think that let me see, what can I say? I think it should be possible. We're not there yet. I think I think that the issue is the following. Maybe it's kind of back to this issue, which is so long as we're constrained to using substrates so far, you have about, as you can see here, 3 or 4% different, about a 3% lattice mismatch or lattice change between the perovskite and the infinite layer phase. And so the growth is kind of a compromise. Do you want to make the perovskite very happy or the infinite layer phase very happy, right? And so in that regard, if we go very far off of this window, probably to the kind of levels that would be relevant for inducing a spin state transition, it's not completely clear to me whether or not we can maintain stability. So that would be kind of, sorry to say, a mundane but very real experimental constraint. So I certainly think this is an exciting idea. I should say that there was also a pressure paper on the archive. So it's a thin film sample, but under hydrostatic pressure, where the main discussion was that the scale of TC apparently goes up quite a bit. And one could imagine at least that gives you a C-axis degree of tuning that could be used. But I think, so right now we can't address that experimentally, but the experimental constraint is really this issue of moving too far away that we can't stabilize. Yeah.
I see. Yeah, any other question from the audience? Yeah, please raise your hand or just ask. Yeah, we have one question from David, please.
Hey, with the multi-band character of this material, would you expect different gaps or on the electron Fermi surface versus the whole Fermi surface? And would that impact your penetration depth measurements or analysis?
Yeah, so that's a very good question. And so, yeah, let me not try to dig around. So indeed, the question has come up in the sense of whether you just have, again, a dominance of the whole band, and this thing kind of by proximity effect goes along for the ride, or fundamentally different symmetries on the different band characters. And so that's essentially, as I alluded to, there's another group who've analyzed their penetration depth in that kind of a language more, that this would be, a combination of, simply speaking, D wave-like and S wave-like contributions. I think what we would, I don't want to speak for them. I think what is clear is that there must be nodal character. I don't think there's a scenario in which we could have a clean gap for the entire superfluid response. But indeed, whether or not one can distinguish between dirty D wave cleanly versus a 2-component order parameter is probably challenging at this point.
Have you tried that at all? So, if you disorder your material, you could sort of pick up a growing quadratic contribution to the.
I mean, sort of, in the sense that we're just trying to make it as clean as possible. So I would say that I could fill you a slide deck with things that look much worse than this. And so just to go back to these numbers relevant for your question. And so again, this is just assuming a clean T-linear nodal response plus this kind of disorder thing. Here's the numbers that we're getting. It's like a third or a half TC. So this is not too bad in some sense, but you know, we'd like to get quite a bit cleaner before we then try to. I think I'm waffling. The point is we're barely clean enough to start doing what we think are meaningful experiments here. And so hopefully there will be a trajectory of improved cleanliness, and that may tell the story that you're looking for. Yeah.
Thank you.
Okay, any other question? Okay, may I have another question? So is there any hope to do RPaths in near future?
Yeah, good question. So actually, we have been collaborating with ZX Shen's group, and there's a paper, I think that's about to be, it's on the archive. So the basic problem, so we could do photoemission spectroscopy. Let me just show you. But angle resolved has not been successful so far. So I think I don't have the right view graph at hand. If you look at the Prisdinium version of this, even without this capping structure, you have much higher crystalline fidelity, but still the first nanometer or so looks like it's doing something a little bit uncontrolled. If we use this capping technique that we do, so in fact, in order to try to get through a thin cap, originally we were trying to do resonant photoemission. You know, other than the once or twice where we thought we saw something dispersive, but it was not quite robust enough to feel confident about, that has been a challenge. So let me say it another way. What are the challenges include that we need to do this reduction step. So one technical question is, can you do this in situ, right? But the second one is, if I use kind of an oversimplified ionic language, this is rather a strongly polar surface. So this is nominally going to be, you know, a layer in here of neodymium or lanthanum or what have you. So 3+, and this is 3-, you know, nickel O2 with monovalent nickel. And so this thing likely has non-trivial surface reconstructions or screening effects that may be important for surface probes. And so trying to control and understand that is probably the central challenge for that. Yeah.
Okay, thanks. Yeah, any other questions? If
you allow me, may I ask?
Okay, please.
But a completely different type. It's about Hall effect.
Okay.
Hall effect is actually a rather tricky problem even in cuprates, but in cuprates at least it's easier because it's only one dominant XY-5 band. Mm-hmm. Either say lightly doped or maybe overdoped and so on. Here you have two components. Is it really clear in which conditions at which doping, at which temperature, the Hall effect is dominated by this extra band, or by this dominant, so to say, band due to Nigel?
So the simple answer is no, we can't really distinguish. And so let me say the following. The issue is that there's not many features to try to play this game. So if I have a 2-band semiconductor or something, the issue is that I might hope to enter a regime of nonlinear Hall coefficient, right? So there are simple games that you can play looking at the magnetoresistance, rho XX and rho XY, to try to pull out these parameters. Mm-hmm. To all the fields that we've measured, the Hall effect is linear. So it's an under-constrained problem in that regard. So, that's the challenge. Obviously, it'd be lovely to see the Fermi surface by ARPAs or what have you, or, we can dream of quantum oscillations in some day or something like that. I think the qualitative statement would be, too many data here, but this is near optimal doping. The Hall coefficient, the raw Hall coefficient, is coming from a negative value and very close to zero at the peak of the dome. So, right, I mean, that would qualitatively say that something like the electron density, electron mobility product and the hole density, hole mobility product is roughly in balance in a two-band scenario. But that's probably all we can say at this point.
But what about overdop regime? Because that actually seems to be the most different from cuprates. In cuprates, you really go to have Fermi liquid, and Hall effect also Fermi liquid like is large Fermi surface and so on. So here it seems to be again, well, insulating like, okay, very bad metal, whatever. So what about tendency and Hall effect in this highly overdop, as far as you can go at least?
Yeah, so these reddish curves here are in the overdope regime. And so the Hall effect has a sign crossing at about 100 Kelvin, right? So this is going from negative to positive. I should say, though, even in the cuprate problem, this is observed, right? So if you look in the overdope regime of 214 cuprates, it is actually starting out negative and crosses zero and kind of flattens out, again, on this 100 Kelvin scale. At least as a non-expert, the Hall effect, even in the overdope cuprate regime, doesn't seem particularly straightforward as well. I think there are lots of interpretations and there's some various materials distinctions, but actually that's what I did on my master's thesis. So that at least data I remember is the 214 cuprates in the overdope regime has a sign crossing as well.
But at least actually naively one would expect that it would be even more metallic. Even in cuprates, it becomes kind of Fermi liquid-like. And here you have, on top of that, you have also extra bands which should make it more metallic and more less metallic. In your case, it's definitely less metallic. Is it at least any ideas why is that?
Maybe I don't understand exactly why you say less metallic, because again, at least in
you said that actually, it's bad metal or almost insulating underdoped and almost insulating overdoped.
Yeah, sorry, I should have been more clear. So that was the case where we were dominated by these extended defects. But in these recent samples, this is the residual resistivity approximately across the series, and it stays low. But let me also take an opportunity to flash one other data. Well, so this is kind of how transport looks now in our cleanest overdoped regime samples. So this is just at the edge of the dome. So this is in orange superconducting. We can suppress that by magnetic field, right? And it's pretty well described by a T-squared fit, right?
Okay.
But there's still this very, it's a tiny feature, but to be fair, there's a slight upturn at the lowest temperatures. And you can see that this upturn feature is still living there that can be suppressed by magnetic field. It's qualitatively looks like localization, magnetoresistance in this regime. But you're right, there are many open questions. I think that, for these samples, we felt confident by a number of checks that we're kind of robust. I think the other challenge for us is that as we go to higher and higher hole doping, what becomes difficult to stabilize is the perovskite phase. And what I mean by that is then we need to go to something like, let's say we wanted to do x equals 0.5. That needs nominally nickel 3.5 plus starting, and then we reduce it down. So again, this whole game is about where does chemistry allow us to play, right?
Okay, very good, thanks.
Any other questions? Oh, okay. If not, let's thank Harold for giving a very great talk. Thank you, Howard.
Well, thanks for
And
having
thanks
me.
everyone for coming.
It's good to see you all.
Thank you very much.
See you.
Yeah, see you, Howard.